We will start the lecture with the point where we left off in the previous lectures. So we had done this example, uh, explained all these values, especially the coherence time, the delay spread time, and their relationships with coherence bandwidth, as well as Doppler spread. So that was done. In today's lecture, start with the statistical channel models. Now, first of all, you could see that Assalamu alaikum Abdullah Salim Saab. You have come very late.
वालेकुम सलाम सर सर वो नाश्ता मैं कर रहा था
अच्छा, all right. So I started the lecture.
जी सर ये अभी हुआ स्टार्ट
Yes, exactly at 1 o'clock. But 1 minute before 1 o'clock, all right. Just started now. So from now on, we will be starting our lectures from 1 to 2:15 because there's no hurry now. So lecture will start just around 1 o'clock. All right. So we had discussed the previous thing which I was telling you, which is now recorded. So today we will start with this section, statistical models, and first of all their philosophy. Why do we use them? Now you have seen that previously the channel values, they were dependent on the receiver's location, velocity, and time. Now what we are interested is in a model that can characterize our exact or actual model over a range of conditions. So velocity could vary, location could vary, time could vary. Now we know that the best thing should be that we should be able to measure the channel taps. But most importantly, we are interested in having a statistical characterization. For example, of how many taps are required, how many values of L from L0 to L1, L2, L3, 3 taps, 4 taps, 5 taps. How do they change? How these values are changing? How much they change? So we just want a statistical model for the exact model which we know is changing. So we require a probabilistic model so that it can match up to the statistical measurements of the channel. Now, what will be our probabilistic model of our channel which can match up with these statistical measurements? So first of all, we have learned in our previous courses, for example, undergrad course of analog and digital communication, that we have a noise model that is given by a probabilistic model. For example, noise was called a Gaussian random variable. And we have, for example, in analog and digital communication, we have found the probability of error of communicating over a AWGN channel or additive wide Gaussian channel. And the error probabilities, they were very much dependent on the independence or the Gaussian distribution of these noise variables. There you could see in the fundamentals of communication or communication systems book of analog and digital communications, that the noise was independent and it was Gaussian, and the system was dependent on these probabilistic models of noise. Now the probabilistic models for Doppler spread, probabilistic models for multipath spread. Okay. The probabilistic models so that they can incorporate these two things for the channel tabs, so the channel filter tabs. They will be less believable as compared to additive noise, because you could see, as you'll be going through this lecture now, additive noise was a very fundamental model. You could read up in chapter 5 of our analog and digital communication book of John G. Prokes and Masood Leahy, Fundamentals of Communication Systems, that we can map or model the random motion of electrons as additive white Gaussian noise. And it's quite accurate, but these models which we are proposing, probabilistic models for our Doppler spread multipath or the channel filter tabs, they will be much less accurate or quite inaccurate, because you could see that we won't be able to model every other channel for every other user. Every user is moving here and there, buildings are changing, you have changing weather conditions and changing environment. For example, nowadays you have this corona epidemic, then you can very well realize you don't have that large gatherings, so all of the channels are changing. They are less believable, but still we need a lot of these models, because without these models we won't be able to test our algorithms, our signal processing techniques that we'll be studying in CLO2. So systems might be designed with experience and experimentation, but first of all, creativity will be stifled, because you say, all right, we have only these models. The second thing is that they will not be able to cover the long or the wide range of different models that every user is experiencing. That is why we need these statistical models. So even with these oversimplified probabilistic model, we can compare our signal processing techniques, system approaches, and get a sense of what type of approaches should be pursued for improving our system performance. So previously, yes, we had studied this white Gaussian noise, and almost all of our work for additive noise or for these wireless channels, they are done with simplified models. Even for WGN, it was only for a very small frequency band. And but still we said, all right, it is better to use to get some sense of the performance. And wireless channel models are quite poor as compared to WGN or additive white Gaussian noise models, but still they provide us an order of magnitude guides to the system design and performance. And you will see that we will be able to define Doppler spread and multipath spread much more cleanly with probabilistic models. There, if you could remember, in the previous section that we were studying, we were able to define these spreads or these the Doppler or multipath spread from the equations or from the multipaths that were reaching us, and we were taking their differences, and Doppler spread we were taking the differences of the maximum two frequencies, okay, that are the most far apart, and they still contribute to a lot of energy. So, but you were never sure that what are those two paths and how they are changing, because every time a user is changing its velocity or he's going here and there, those values are changing. But with these probabilistic models, we will be able to define them much much clearly or cleanly as compared to our previous deterministic models. But we still have a problem. The channels are very different and we cannot really characterize them by a probabilistic model. But at the same time, there is a huge literature of probabilistic modeling for the wireless channels, and it has been highly useful for providing insight into wireless systems. So we have pros and cons. We have benefits and disadvantages, but overall, the advancement in wireless technology has come with the help of these probabilistic models. So we will be pursuing these statistical models so that we can test our signal processing techniques on them. And we must be able to have a clear mind about the robustness of these results. So once we make up a probabilistic model, the results will be applicable to that model or to any real-time model that can be simplified to our probabilistic model. So real-time environment is quite complex, okay, and you can simplify it to one of the probabilistic models which will be studying. First of all, what to model? So you know this equation. This was a time linear time varying channel. The delays were changing and the magnitudes of the different paths were changing. Then we discretized this model as well as converted into a discrete time baseband model. It became this model, and finally our HLM comes out to be something like this. So each tap, any Lth taps, you might have 5 taps, L will be going from 0 to 4, or L will go from 1 to 5. So one tap for our discrete time baseband wireless model is given as follows. So you can again see this each tap is actually sum of the contribution of many paths. Each path has ith magnitude, it has ith time delay giving us ith phase, and then they are smoothened by the sync function, okay, that is operating at roughly around tau w or around the order of bandwidth w. This we have all studied just as a revision. So we will be trying to use statistical models for these channel taps. And again, you can see that as each tap is made up of a multiple of paths, so we have a very strong probability that our statistical models will have a good chance of success. So now we will see the Rayleigh and Ricean probabilistic models, one of the simplest as well as used in a lot of research as well as system performance evaluation. Now, the simplest model for these filter taps is based on the assumptions that there are a large number of statistically independent reflected and scattered paths. So there are a lot of paths. Okay, all these paths are independent from one another. A large number of paths. Paths could be reflected signal or scattered signal. Okay, and their amplitudes
सर
of the
आवाज बहुत
paths.
कट रही है आपकी.
अच्छा. ये आप कितने स्टूडेंट्स, 4 स्टूडेंट्स आ गए माशाल्लाह. शिराज साहब भी आ गए हैं, अकील अहमद साहब भी और मोहम्मद साद. अच्छा, अच्छा हाँ जी, all of you can hear my sound. Now there are 3 students. हाँ जी, all of you can hear my sound now.
Yes, sir.
अच्छा, हाँ जी, everyone was feeling that the voice was being you know
Yes, sir.
Disturb. Yes, everyone.
Yes, sir.
Acha, acha, acha. All right. So you can always stop me. You can give me messages that the voice, or you can just speak up that you are not able to hear, so that we can cover that fault, because we are speaking on the internet or communication channels, and these channels have a problem. All right. So uh, we are now studying one of the statistical models, Rayleigh and Ricine channels, and the simplest model, or the probabilistic model, assumes that we have a large number of different multipaths. These paths could be reflected or scattered signals. All right. So their amplitudes are a random number. Okay. Amplitude of each path. All right. Remember that the tap is made up of multiple paths. I is one path, and you have multiple. And now each path, this is each path, each ayat path. Its amplitude is a random number. All right. So sometimes you will be getting, let us say, 4 volts, just for example. At some other time, it will just go to 3 volts. It will be following some type of random distribution. But it is random, it is changing, it is not deterministic, you cannot determine it. Now the second thing is that this phase is this thing, you can see very well, and it is 2 pi. If the phase go 5 pi, it is just can be mapped from 0 to 2 pi, no problem. Now this fc tau I can be written as di over lambda. You can also see in my notes, fc ti can be written as di over lambda. How can it be written? Because that lambda is equal to c over fc. All right, wavelength. Fc goes above, di over c is actually equal to tau I, the delay time, distance covered c. In the models previous, we used to have r naught, then we have r naught plus vt, and so on and so forth. It could change. All right, we are just writing as fc tau I as di over lambda. Di is the distance covered by the path. It might be r naught, I naught, be whatever the length covered by that path. So these reflectors and scatterers, which are reflecting the path or scattering the path, we assume in our simplest probabilistic model that they are far away relative to the carrier wavelength. So these distances di, which is distance traveled by, these distances are quite large as compared to the wavelengths, and it is quite reasonable. You could very well see, the wavelength is in centimeters. All right. And the distances, you could very well see from a good reflector, will be definitely in meters. So it will be definitely greater than 100 times. Right? It might be in kilometers, but just for sake of simplicity, it will be more than 100 times greater. Now, if these distances are quite large, all right, then it is reasonable to assume that the phase, total phase, for each path is uniformly distributed between 0 to 2 pi. All right. So phase for each path is now a random variable. It is now a uniform random variable. Okay. And every different path has also a phase contribution, which is also a uniform distribution, but it is independent of the distribution from the first path. And it is also makes sense, because once, let us say, you have a building that is reflecting, it will be independent, let us say, to some billboard that might be some place somewhere else. All right. So both of them will be reflecting or scattering. Okay. And that reflection and scattering will change as if you are moving, so that those values will be changing. And in this way, we can assume that the phase is uniformly distributed, because remember, we have to have a general model. So any reflector could give you any phase shift. All right. And at some other time, it might be giving you some other phase shift. Secondly, the phases of the different path, they will be independent. Definitely they will be independent because every path is coming from a different scatterer or a reflector. So yes, they will be independent. Now, this each contribution of ith path into making this HLM can be modeled as a circular symmetric complex random variable. Haji, every one of you remember what is a circular symmetric complex random variable?
No sir.
सर हमने कॉम्प्लेक्स रैंडम वेरिएबल नहीं पढ़े
रियल मॉडल्स करवाए सर रियल
रियल
रैंडम
मॉडल्स पढ़े हैं कॉम्प्लेक्स मॉडल्स नहीं पढ़े
सही बात चलो ठीक है अच्छा just as a question now I'm happy that there are 4 students in my online class I think all of you have registered on the LMS
yes sir
अच्छा अच्छा Akil Ahmed are you also registered
यस सर मैं भी रजिस्टर हो गया हूँ
अच्छा आप भी हो गए चलिए शुक्र चलिए वेरी गुड all right let's go back to the lecture acha so let us try to understand and actually now I tried to find a lot about this circular symmetric complex random variable and all the discussion in the book is about the vectors circular symmetric complex random vector or Gaussian circular symmetric Gaussian complex random variables or vectors so I couldn't find much information in the books or in the web about this complex random variable so I have actually made up my notes so to end this confusion once and for all right now please bear with me and this is my unique way of trying to make you understand this is the first time I've tried to make up these notes so that this confusion is solved for every student or for any incoming students in the next sessions. Now let us try to understand what is happening. Now please see that each path, okay, you know the amplitudes, all right, they are slowly varying that we all know and it is well discussed changing in seconds and all that. And yes, the taps that we have also realized they also take a lot of time, okay, and you can see in the last example that we have done extensively. Okay, we have discussed, we have spent a lot of time that for a path it is taking to move over a tab is 20 seconds. All right, amplitude is changing in 1 minute. All right, but phase change is 5 milliseconds. So main thing which is changing or drastically changing, okay, is path phase. All right, 5 milliseconds that we have all discussed many times. So we won't be going into that now. With that knowledge, all right, now I know that my path is given. So this is almost a constant, I can assume, all right, for that millisecond time. This is almost constant, you know, minute change. This is changing. So I can just assume for making a simplistic model that this is almost constant. And yes, the phase is changing, right? By milliseconds, your the phase is changing. It is giving you new and new values. The phase is changing like a uniform random variable with all that discussion. Now, you have studied in your previous probability or stochastic course. Let us say that I have a stochastic process. Let us say the magnitude with cost. Now here you can say that what is happening. You can this constant becomes some amplitude and you can open this EJ and it will give you cos and sine. Cos for the ith phase and sine for the jth or the quadrature phase. All right. So let us assume that the ith phase is a cosine theta t, where theta t is a uniform random variable. Now, if I try to find its mean, all right, then you can very well see finding its mean. You know, a goes out. Uniform random variable taking values from 0 to 2 pi. This will be 1 over 2 pi, and this is the function of the random variable. You know, this 1 over 2 pi. This goes out. And integral of cos t will be it will be sine, all right, and this will be 0. So its mean is 0. Similarly, if I try to find its variance, its mean is 0. Variance will be, square. I'm trying to find the variance of the real part of my ith path's contribution to the HL tab. So this becomes like this, and this becomes like this, and cos 2 pi mean is 0 because you have 2 cycles in in that 0 to 2 pi range. So this will be definitely 0. So your variance is a square over 2. Now if you try to find again the mean and the variance for the quadrature phase, you will again get 0 mean and a square over 2. Second thing, this means that both real and imaginary, they are identical. One thing. Second thing, you can also note that they are both independent, and this can be very well verified. For independence, you take the two functions, just ignore a square that is there. Mainly we have to see independence. So you can see that once you multiply, this becomes cos 2 theta, and again cos 2 theta will give you definitely 0. All right, provided you integrate it over 0 to t time period, and this will give you 0. So now we have each path that is identical. Each paths, real and imaginary, are identical, and the two paths are independent. So they are making up the real and imaginary are IIDs, in the identical independent distributions. Now, all right, let's go further. He says now that this IID can now be modeled as a circular symmetric complex random variable. First question is, what is a circular symmetric complex random variable? So again, I have tried to explain this in my notes. So what is a circular symmetric complex? So remember, I am now saying circular symmetric complex random variable. You cannot circular symmetric complex Gaussian or complex normal. No, I'm not putting normal. That will come in the next step. First of all, we're trying to understand circular symmetric complex random variable. All right, what is the definition? The definition is very simple. That if you let us say x is a circular symmetric complex random variable, you multiply x with some ej theta, then this is a new random variable. The mean of that new random variable will remain equal to the mean of the random variable of the original random variable. This can only be possible if the mean value of the original random variable is 0, because 0, 0 on both the sides, this will still remain 0. The second condition is that, all right, so the condition for circular symmetric complex random variable is that if you multiply, all right, the circular symmetric random complex random variable x by ej theta, the distribution does not change. The mean will remain the mean, the variance remains the variance. Or let us check with the variance. So variance of our new random variable is given by e of x square minus mean of new random variable, and thus this must be equal to the mean of x square minus mean of x of the old random variable, that was x, and its variance is sigma x square. Now we know that the means are 0. This means that this sigma square is equal to this thing, and this is equal to this, and this. So this means that both their ex squares, they must remain the same. All right, very good. Now how can that? So let us say that we have already shown that my x is a IID. It is a complex random variable, but I now have to show that it is not only a complex random variable, but it is a circular symmetric complex random variable. Or let us try to show. So for that, I've shown the mean. Now I try to show the variance. All right, so here you could see very well that the mean of x as well as the x is equal to a plus jb. So mean of the real and the imaginary part, they have to be 0 because e of x is 0. So both the real and imaginary, they must be 0. So now I write it like this, e of x square. Now what is, remember that x is a complex random variable. So its x square will be given as a plus jb into a plus jb conjugate. This becomes exx conjugate, this becomes ex mod square. And what is ex mod square? If x is equal to a plus jb, so its magnitude will be a square plus b square from the Pythagoras theorem. Now at the same time, if I say, what is the variance of my x random? We know it is ex square, and ex square is just is equal to this. So we have found the variance of our complex IID random variable, which is this. Now let us try to find the random the variance for ej theta x. This will be ej theta x. There is one mistake. This will be a plus j beta. So please correct it in your notes. All right. So e of ej theta x whole square will be this thing because it is a complex number times its conjugate, which is this, and then this becomes again x mod square, and we have found x mod square that is equal to a square plus b square. This means that the variance for this new random variable remains the same as the variance for the original random variable. So you are just multiplying. This was some real part and some imaginary part, but you are just multiplying with a phasor. You haven't any magnitude. You just multiply with a phasor with this complex number. All right, and there is no change. The distribution remains the same distribution. If this definition is satisfied, that the mean remains the mean, the variance remains the variance, or the random variable is invariant to a phasor shift of ej theta, then that complex random variable will be called a circular symmetric complex random variable. Ji, everyone is understanding? This explanation you will never find. I tried to search a lot, but I couldn't find. So I have made this up so that we can now connect with this concept of circular symmetric constant random variable with other things. Ji, is everyone understanding at this point?
सर ये तो कांस्टेंट हो फिर भी ऐसी बात फॉलो होती है, नहीं तो सर मुश्किल हो जाता है एक रैंडम वेरिएबल के लिए उसके आप फेज शिफ्ट करें और उसको ये नहीं के, तो सर ये कांस्टेंट है या नहीं?
Which is constant? Which thing is constant?
सर प्रोबेबिलिटी डेंसिटी फंक्शन.
Probability density function. You know what is the probability density function?
Of x.
Probability density function g of x. Yes.
Yes.
What we are saying, it could be any random variable x, but x will have a real part, x will have an imaginary part, and the real and the imaginary part, they have the same mean and the same variance. They are identical, but at the same time they are independent. They could be a Poisson distribution, they could be Gaussian distribution, they could be Bernoulli distribution, they could be binomial distribution, they could be any distribution. All right, but they have to satisfy the IIDs. Now once they satisfy the IIDs, then we say that the same distribution will remain the same. If you make a new random variable by just applying a phase shift, by just multiplying the original random variable by this ej theta, the new random variable will have the same distribution as the previous x. That is what we are saying.
Sir,
So
page number.
the x random variable is invariant to the phasor shift of ej theta. हाँ जी, क्या कह रहे हैं आप?
सर पेज नंबर 3 पे जाएगा जरा, उधर एक पॉइंट डिस्कस करना है। पेज
किसका
नंबर 3
पेज
इसी
नंबर?
सर इसी लेक्चर नोट्स। जी जी सर थोड़ा नीचे सर, ये जो लिखा हुआ आपने ई एक्स जे थीटा इज इक्वल टू ई एफ एक्स, जहाँ सिमेट्रिक आपने किया हुआ जी, इसी पेज की फर्स्ट लाइन।
हाँ, ये तो मैं प्रूफ करना चाह रहा हूँ ना, ये तो अभी
जी
इक्वल टू प्रूफ करना है। ये मैंने
हाँ
एक्चुअली
सर।
अपने यूनिक स्टाइल में इसको लिखा है भाई,
जी
ये साइड है, ये साइड, हमने दोनों को बराबर दिखाना है। और अभी
हाँ
मैंने
सर।
लिखा हाउ, कैसे होगा, फिर आगे मैंने बराबर दिखाया। हाँ जी
सर फर्स्ट लाइन को मैं डिस्कस कर रहा हूँ, जो फर्स्ट लाइन है ई जे थीटा जी, ये इक्वालिटी कैसे मेंटेन करें?
भाई, ये अल्लाह के बंदे, ये तो कंडीशन है ना, ये कंडीशन है। एक सर्कुलर रैंडम वेरिएबल की कंडीशन ये है कि उसका मीन सेम रहना चाहिए, इट शुड बी इनवेरिएंट टू द फेज शिफ्ट। बट हाउ इज दिस पॉसिबल? दिस इज नेवर पॉसिबल, बिकॉज देखिए ना, ej थीटा विल कम आउट ऑफ e। यहाँ पे ये याद रखें आप, एक्स रैंडम ej थीटा तो कोई फेजर शिफ्ट है ना, ये तो कोई कांस्टेंट नंबर है, कोई फेज है, 2 पाई हो सकता है, पाई बाय 2 कुछ भी है, फेज है ये बस। ये कोई रैंडम वेरिएबल तो नहीं, ये तो e से बाहर आ जाएगा, तो फिर ये बराबर तो कभी हो ही नहीं सकता। इट कैन ओनली बी इक्वल व्हेन ex इज इक्वल टू 0।
सर मतलब ये डिराइव्ड फॉर्म नहीं है यानी?
ये आपको समझाया जा रहा है ना
सही तो
कि
प्रॉपर्टी है
फॉर
ना
अ
सर्कुलर की।
हाँ, दिस इज अ प्रॉपर्टी, हाँ दिस इज अ प्रॉपर्टी, but this property can only be true if this is 0.
यस सर,
ओके सर।
यस।
This is the thing, and you know that x is also a मतलब अभी चूंकि हमने कॉम्प्लेक्स रैंडम वेरिएबल बनाएंगे तो फिर सर्कुलर सिमेट्रिसिटी बनेगी, इसके लिए तो आपको चाहिए this is, we know x is a plus jb, this means ea and eb, they both have the mean 0, so that is why ex is 0, all right, and that is why this is true. So circular symmetry के लिए कंडीशन ही है कि that random variable must have 0 mean.
यस सर।
Now let us go further, step by step. All right, again this explanation you won't find. Achha. Now we know that every ith path is a complex random variable, you know, because of this thing. Now we have seen that the real and imaginary part of each ith path of HLM is independent. We have just seen sine cos independent. And we have also seen that the real and imaginary part of each ith path is identical. Yes, we have just seen they have the same variance and same mean. That is their IIDs. Now, all of those ith paths, they are summed up to give me HLM. All right. So, from the central limit theorem, if you have a large number of independent identical, I think you all have studied the central limit theorem in your probability stochastic course. So if you have a lot of random variables that are independent and that they are identical, and when you add them up, what you will get?
Gaussian.
Gaussian. That is the rule. So now the real part will add up, the imaginary parts will add up, and they will become a Gaussian in real. They will become a Gaussian in imaginary. They are already circular symmetric. You are adding them up, they will again give you a circular symmetric Gaussian random variable. Previous properties they will just transfer. They will now become a Gaussian random variable. So now you have a circular symmetric complex normal distribution, or you can say circular symmetric complex Gaussian random variable. And again, we have also discussed that, but in the here I've explained a complex Gaussian random variable whose real and imaginary are IIDs. We have done all of that. It is complex, it is not Gaussian, it is IIDs. They satisfy the circular symmetry property, that is ej phi x has the same distribution as x for any phi. and all that.
सर एक सवाल है
यस आप प्लीज पूछें ताकि हम आगे चल सकें.
सर
Please
सवाल
ask.
ये है कि सर ये हम सर्कुलर सिमेट्री क्यों देख रहे हैं
Why we are saying that we are seeing circular symmetry?
यस
Because what we are saying that if we take this type of model where the phase is a uniform random variable, all right, then the paths, the taps, they become circular symmetric, complex symmetric Gaussian random variable. So that is why we are saying, because if we take this type of model, then the taps, they become circular symmetric complex Gaussian random variable. That is why we are studying that, because the taps are coming out to be that thing. This assures that this is in fact circular symmetric, and we have seen how can we donate circular symmetric, because circular symmetry just need the mean, all right, and you just need to show the variance, and you can see the variance is actually a square plus b square, as I've just told you. The a square plus b square, all right, the mean of a square plus b square. So it is it incorporates this variance of the complex, incorporates the magnitude of the real part as well as the magnitude of the imaginary part. So this sigma square is equal to, the squares of both of them, as we have seen here. This thing. Sigma square is actually incorporating e of a square and e of b square, and we will see that actually a and b, they are both independent. This will become e of a square plus e of b square. This will also become in the next lecture, but just at this time I just wanted to tell you a very important question that also comes in exams. That a question is how can you say that HLM is a circular symmetric complex Gaussian random variable? All right. So each HLM will be standing for each different L, and it will be an independent complex for all that, Cn and this thing. Now, very, very important point. Let us check your previous knowledge. If I say that each HLM has its X and Y, all right, like a complex Gaussian random variable and all IIDs, they are independent. It is a Gaussian distribution. Then what will be the magnitude of this channel? Now again you can see our previous course book, which is Fundamentals of Communication System by John G. Prokes and Masood Slehi, chapter 5, where he shows us that if x square and y square under root, that is the amplitude of the channel tap, because channel tap is x plus jy. For our, this is for a plus jb. So what is the magnitude? Magnitude is under root x square plus y square. And what is the phase? The phase is tan inverse y over x. And you can see there, all the derivation is there. That then, वो ये सारा आपने करना है. मैं इसको आप जाके हम बुक में देख लें, मैं आपको शॉर्ट में बता रहा हूँ कैसे किया जाता है. You make two functions of these two random variables. One is representing the magnitude and one represents the phase. You find the joint distribution of the magnitude and the phase in terms of the joint distribution of x and y divided by Jacobian. Okay, all of the details are given in the book. You will get the joint distribution of magnitude and phase. Then if you integrate this by the phasor, you will get the magnitude distribution. And if you integrate the joint distribution by phase, you will get the magnitude. Vice versa, if you integrate this by magnitude, you will get the phasor distribution. So phase distribution will come out to be the phasor distribution comes out to be a uniform distribution, and the magnitude distribution comes out to be a Rayleigh distribution with this thing. So this in turn gives us a very good proof that the phase is uniform distribution. All right, and the magnitude comes out to be Rayleigh. Another thing that you have to do is that what is the distribution of HLM mod square? So HLM mod is under root x square plus y square, but HLM mod square will be just x square plus y square. Again, apply the Jacobian method, joint distribution with that same phasor, and you will be able to show that the square of the magnitude is equal to this. So these distributions are fundamental in understanding the performances of our wireless systems when we will go into the next chapter. So this you have to do, and this has been also asked in many exams. In last exam I had asked this thing for the I grader. Many times this has been asked in the previous exams, so you have to go through them. Previously, you know, students didn't used to study all of this, so I had to do all of that. But now that is why the prereq is stochastic processes, so that you can do the derivations. This derivation is available in the book, so please go through it. And this you have to do it yourselves. But still, if you have problem, I have my notes, because I have just given this problem as you know, as as a quiz problem in Punjab University. Then I also gave this problem in the comprehensive exam of an I graded student. So I also have the solution, but I will prefer that you do it by yourselves. This is called the famous Rayleigh fading. All right. So whenever you say that I'm checking my model on a Rayleigh fading, this means that actually you have a large number of reflectors or scatterers. All right, and all of them are giving you paths that are independent. Their phasors are uniform. The main thing is phasor is uniform, and that uniformity actually comes out in a circular symmetric IID, all the IID, which comes to be a Gaussian circular symmetric IID gives you circular symmetric gives you Gaussian, and that Gaussian gives you Rayleigh fading or exponential fading. This is a huge step that you have now taken in understanding the wireless systems. But this is not the only model that is used. Another model that is also used is this model. If you could see here, this is the same circular symmetric model, but this model has an EJ theta. So EJ theta, it says that it has one path that is a direct path. Okay, so you don't have those summations here. The signal is directly coming with this phasor EJ theta, and these are just the ratios. So K factor K plus 1 energy goes into the direct path, and 1 over K plus energy that goes. But if you add the those just the magnitudes, you can see square, this will become K plus 1 over K plus 1. The energy is the same, but we have divided that 1 over energy goes to the scattered path, and K over this energy goes to the K over K plus 1 energy that goes into the direct path. So this model is also used once we have a direct path. And this is the famous Rayleigh model. And all that you can see here. So this is actually a better model. Now we have to see that, all right, we have made our Rayleigh or Rayleigh model depending on whatever the circumstances and all that. But we need to know the coherence time. We need to know the droplet spread, the coherence and all that. How can we found? Previously we had those models and we were using those calculations, differences and all that we discussed in the last lecture. But how can we find from these? All right, from these models which are more realistic as compared to the previous model. Previous model, we just said assume that one wave is coming like this, and here we have a processing model that is actually much more matching with the actual real model, which is very, very complex. We are just trying to model that statistically. Now what we say, you define this thing. This is called the famous autocorrelation function, and I think you all of know autocorrelation function in your previous course. Again, we don't have to go through it. So what is if we have a Whiteson stationary process, then its autocorrelation is given as follows. So it is this is tau. Tau is n here, this function of tau. This will be t and this will be t plus tau. So this mean will give you the autocorrelation function. So now here we are assuming that the taps, okay, they are not function of time. Actually they are function of time, okay, all right. But let us say that we are speaking about those 20 seconds in which for 20 seconds coherence time the channel is almost the same. For that time we can assume that it is not changing, all right. Now so you can see that the sequence of random variables HLM with this autocorrelation function will have a mean, yes, it will have a covariance function, but the covariance function is not dependent on m because we have just taken this m out. So once you take this m out, this becomes a White-Sands stationary process, and you all know that from your previous course. Again, we won't go into details. Secondly, we also know that HLM for one path is independent for HLM for different path, because one HLM for one path, for one tap is a sum of certain paths, but another HL dash for some other tap, it will be sum of different paths. It could be, let us say 4 paths are contributing to this HLM, and the 10, 100, or let us say 10 paths that are contributing to HL dash, they are completely different paths. All right. So they are independent. We can very well assume that these HLMs are independent. And that is written that intuitively possible since paths in different ranges of delay contribute to HLM for different values of L. Also seen in the the figure, different paths were contributing to one one Lth tap, and you can see the diagram also from your previous lecture. And that he is right that one reflector might come into the other tap, but if it wants to come into the other tap, it requires 20 seconds to move from one tap to another. So by that time we don't have to worry, because our random variable will have given us enough values to do all of detection and demodulation, so we won't be concerned. For that, next time we will have next values. So channels are changing, but we can assume that we are working in that coherent time. So in that coherent time, we can well assume that it is a White-Sands stationary process. Now, so the coefficient RL0, RL0, which means the energy. If you have this N0, so you're just finding H conjugate with H conjugate. So, H E of H square. This gives you the energy. If the mean is 0, this will be giving you the variance also. This is the power. So it is proportional to energy power received in the Lth tap. So now I am defining my time delay. So time delay, so I was written this in my notes here. So this is the time delay, will be given as 1 over W, time delay 1 over W times the range of L. And what is range of L? The values of L for which the energy, most of the energy is contained in that range of L. For example, if I take L is equal to 100, but that R100 for 0 has very low energy, so I won't take it into the range. Okay? So I just take that range of L for which I am getting good contribution in the total energy. All right. Divide that by W, this will give me the delay spread. And we have just seen this. Yes, this will give delay spread because this tau W is equal to L. We have seen that tau W is equal to L. That contributes to the sink part, and that gives you the number of taps. Very good definition of delay spread from the probabilistic model. Now, second thing, how is I can define the coherence time? For the coherence time, I will see, all right, no, yes, you are right, RL can change now. Okay? With respect to time, RL can change. So he says, all right, what will be the time when my RLN will change significantly as compared to RL0? And we can define the significance, all right, 5%, it is 95% has changed, or 100% has changed, you can define that. But again, you will get a value, and we will also do one example, so it will become clear. Last thing is, what is the effect of W? The bandwidth of the channel that you are trying to take. But we know one thing, and we have seen in the last lectures, that 1 over W, it determines the change in the windows. All right. And yes, if you will be increasing W, yes, the taps will be becoming narrower, because 1 over W was a difference. L minus tau W. So 1 over W was the main point difference between the two taps. If you will be increasing W, that difference you could very well see will be decreasing. So what will be happening now? Previously, if you have less low value of W, then 1 over W is large. All right. So all the paths were coming in and they were giving you one tap. And your Rayleigh approximation, or the approximation of the Rayleigh channel, that you have a lot of paths, that was very good. But once you are increasing your W, so what is happening? That your taps are becoming narrower and narrower because of increase of W, and 1 over W is becoming smaller and smaller. So you are getting a good smaller picture, but you are increasing your taps. But at the same time, you are getting out of the Rayleigh approximation. You are not applying a proper Rayleigh approximation. So your information becomes questionable. Last topic is the famous Clark's model. Again, this has been used and this will be used in our next lecture also. Very popular model for flat fading. We again say transmitter is fixed, as we have done in the previous lecture. Mobile is receiving, is moving with velocity v. All right. And the transmitter signal is scattered by a stationary object around the mobile. So there are a lot of, previously we had just one reflector. Now we have a lot of scatterers, also a lot of multipaths are coming. Let us say there are k multipaths, and we say that each path has this phase. All right. Each path is arriving with this phase. All right. With respect to the direction of motion. So this is the various theta phases that we are getting. So K is very large, lot of paths are there. So scattered path at the mobile with angle theta. So every path is coming with theta I. It will have a delay corresponding to that theta. Let us denote that by tau theta. This will be our model. So every ith path has a delay tau theta corresponding to its theta, and the magnitude will be corresponding to that theta part will have some magnitude A. And so we assume that we can have different scenarios, that these A could be some numbers, but here we will take the most common scenario, and that is that power is equally distributed in all the paths have equal power. All right. So the amplitudes of each path is A over under root K. This means, the energy power will become A square over K. All right. And summing this up over all, this will come out to be just A square over K into K. This will become A square. All right. So this I have also shown in my note. So if someone has any problem, ये मैंने पहले show कर दी थी, ये देखें A square बन रहा है. Now, so the scatterers are situated like a ring. All right. And this is also shown in the figure like a ring. So there are, now remember, this is a one ring model. You don't have one reflector. You have a lot of scattered paths that are coming like a ring. and receiving energy is A over or A square over Q along a small fraction of the total energy. Now, in this model, we assume, please, very important, W is much smaller than the reciprocal of the delay spread. What this means? This means it is a flat fading model. You will say, why, sir? You will say, all right, because of this tau t. Because tau omega, that will now be 0. Because we say omega is much, much less than 1 over tau, as written in our assumption. That W is much smaller than the reciprocal of the delay spread. W is much smaller than the reciprocal of the delay spread. So this means that this is a very, very small than 1 over tau W. So this means a very, very small number as compared to tau. This will be making it 0. Once tau W is 0, then only L is equal to 0 will work. L is equal to 1 will not work. L is equal to 2 will not work. You will have only one tap. And HLM will be reduced to H0. H0 corresponding to L0. So you will have only one tap. It will become a flat fading model, not a frequency selective model. So your model will not have that convolution, just H0 into X plus noise. Very simplified model. H0 because L is 0. That is why it is 0. And M minus L, L is 0. That is why only this is sufficient. Now we said the phase is arriving from this thing, 2 pi tau theta. All right, ये तो सारा कुछ पहले हमने पढ़ा है. Now we make the assumption that this phase, total phase, is uniform distribution. This phasor is uniformly distributed in this thing and independently distributed across all the angles. So we are trying to, make it Gaussian. All right. So you can see what is happening, how we have gone from a model that we had started for in the beginning of our course. Okay. That was a deterministic model. But first of all, we added a lot of paths in our model. And all those paths, they were giving you definite thetas. Those thetas were, let us say, the angles corresponding to your direction of motion. Let us say I'm moving, let us say, in the x-axis. So one path, let us say, is coming along x0 axis, or we can say its theta is 0. Or we can say phi 0. अगर आप electromagnetics थोड़ा सा जानते हैं. All right, phi is 0 along x-axis. Let us say other angle is phi is equal to, I don't know, 45 degrees. Next is 90 degrees and 135, 160. So the angles there, they were distributed. Yes, they were distributed around 2 pi. All right, but they were numbers. Those numbers were giving me delays or taus. Right? And then I made my model. In this model, still I have, all right, a flat fading model, but at this point they were still a fixed time thetas and fixed taus. All right, but now I am trying to shift the step that we have taken in this lecture. We are trying to shift our model from a real model to a probabilistic model. So there I have to put some random number. And how can I do that? So I do that assuming, as I've already seen, that actually the phase magnitudes, they are really, so the phase, they actually vary as a uniform random variable. So I say now the assumption is that phase is uniform. And uniform means that across all the angles you have uniform distribution. Any angle can come. All right. Now, each tab, we have only one tab now. Now one tab, you know, it will be actually sum of all those independent paths, okay, that have a uniform phasor distribution. And we know, we have seen all that they will become a Gaussian random variable. They have all that. So they will become a Gaussian process. And its autocorrelation can be shown to be like this, where this is the Bessel function of the 0th order. The first kind Bessel function 0th order, and this is given as follows. If you will have studied in your previous ADC course in terms of, you know, frequency modulation. And D is the droplet spread. And you can see this droplet spread is the same spread that we have seen in our model when you had a reflector and a direct path. So here the reflector, here actually we have scatters, a lot of paths, but the droplet spread remains the same. And you can take its, you know, inverse, or you can take its Fourier. And you know, the autocorrelation in your previous course, that autocorrelation Fourier gives you the PSD, power spectral density. All right. And both these functions are shown. This is the autocorrelation function, and this is the PSD of our Clark's model. Now, we have done, we need to know what is the coherence time. So we have, let us say, the coherence time is a time when my autocorrelation changes by 95% of the time it was available at n is equal to 0. So this n, this will give me a sense of my coherence time. So again, he has omitted some steps which I have done. You can see in my notes here how to find it. So we have R0 should become only 5% of original R0, but I know that R0 n is given as follows, as you have just seen. So R0 0 will be J0 n 0. This will be J0 0. So I put this value here. All right. So R0 n will become equal to this 0.05% of J0 0. And then I put the value of R0 n. A lot of things will cancel. And I know that n over W, this is my coherence time. So this is the nth time. You know, 1 over W is the sampling time. So n into this may give me the coherence time. That the coherence time at that nth corresponding time, I will be getting 95, only 5% of my original value. So become TC and J0. You know, you can see in the book that the Bessel function, 0th order Bessel function. You can see also here, you can J0 when beta is 0. So the 0th order, and you will get a value of 1. This will be 1. This value is 1. This is 1. This comes out to be, so J0 inverse 0.05 divided by pi ds. This will give me TC. So remember what was the TC that I was getting in the last lecture? In the last lecture, the TC that we were getting was 1 over 2d. You could see there, coherence time was related to ds. 1 over 8, 1 over 4, 1 over 2. It could be anything depending on the model that you had applied. But now we had applied a similar model, but it has a lot of scatters, and we deliberately made those scatters giving you uniform phase, and now we have a TC defined based on the probabilistic model. So, and these discussions are done in the, and he says that you can see here again the very good thing that the droplet spectrum, or the, you know, the phasor or the power spectral density, you can again see after the droplet spectrum there is no PA power. All the power is in between here. All right. So he has discussed some of these things in 2.17 that you can do it yourselves. Hence, finally, we have completed this chapter. So it took us about 5 weeks or 10 lectures. But actually, we were 1 week. Actually, I should have completed in 4 weeks, but it took me 5 weeks because I also spent 1 week in introduction. So to get you a idea of you know, the systems approach in order to study this course. If you have any student any questions, you can ask. Else I will go to the attendance. Any
Sir,
question you can ask?
Clark's method जो क्लार्क्स मेथड है, ये होम असाइनमेंट है, मतलब कि खुद से
नहीं
करना है?
नहीं, कोई होम असाइनमेंट मैंने आपको, वैसे आप जितनी मर्जी कर, मैं जो आपको बताता जा रहा हूँ आप बिल्कुल करते जाएं, साथ साथ जो भी बता रहा हूँ, मगर मैंने एक ही आपको असाइनमेंट दी 10 मार्क्स की, जो मार्क्स वाली है। बाकी तो आपने बहुत सा काम करना, मैंने लास्ट सेक्शन में आपको बहुत सा इंपॉर्टेंट काम दिया था, इस सेक्शन में मैंने आपको बहुत सा इंपॉर्टेंट काम दिया, वो अपने तौर पे करते जाएं, कोई मना नहीं है आपको, आप जिस तरह मर्जी करें। मगर अभी जो असल चीज़ बताने की है कि एक आपको होमवर्क दिया हुआ है, वो होमवर्क का मैं सोच रहा हूँ कि उसमें जो है ना एक ये नोट भी डाल दूँ कि जी अगर मुझे प्लेजरिज्म मिल गया तो -10 लग जाएगा। ठीक है, मुझे वो लास्ट टाइम हमने भी अंडर ग्रेड में किया, लोग आपको पता छापे मारते हैं काफ़ी ज़्यादा, तो हमने भी जाने दिया, मगर अभी मेरे ख्याल पीछे से इंडिकेशन आई कि जी नहीं आपने सख्ती करनी है, और मास्टर्स को तो वैसे ही हम टॉप ऑफ द यानी कि क्रीम ऑफ द क्रीम बनाना चाहते हैं। तो ये आपको ये बताना है कि जी आपने बिल्कुल खुद से करना है, जितना भी समझ आए, जो आपकी प्रॉपर्टी की पिछली नॉलेज है उसको अप्लाई करके करें, और जो यहाँ सीखा आपने, और इसमें प्लीज़ आप एक दूसरे से डिस्कस कर सकते हैं, मगर रास्ता आपका अपना अपना होना चाहिए। So if I find any sentence that is repeated and on anything that is being repeated again and again, or the sentences that comes out, they come out naturally different. So this is one condition that I will apply. So I might made those changes in the, but the problem will remain the same, but I will might make those changes in the assignment that you shouldn't do any plagiarism. Any other question?
सर असाइनमेंट पेजेस पे करके या वर्ड फाइल बना के सेंड करें आप?
नहीं, इसमें आपको पता होना चाहिए कि व्हाट इज द प्रोसीजर, सो आई विल जस्ट रिवाइज दैट. So you could see in MS Teams you have a folder, all right? So you will do your assignment on a piece of paper, then you will take its scan image, and then you will upload the scan image onto the MS Team folders.
Okay,
all right,
sir.
This is the procedure that you have to adopt.
Yes, sir.
अच्छा, I
Sir,
want to say जी
एक क्वेश्चन है सर।
जी पूछें.
सर जो आपके नोट्स थे सर उसमें जे इनवर्स लिखा हुआ था एक जगह पे, तो सर
हाँ जी.
वो कैसे कैलकुलेट करना?
वो अच्छा, आप भूल गए मेरे ख्याल से. बेसल फंक्शन का इनवर्स कैसे निकालते हैं?
किसका सर? बेसल का
बेसल
हमने नहीं पढ़ा हुआ था।
बेसल फंक्शन आपने एडीसी में नहीं पढ़ा, आपने पिछले अंडरग्रेड में, आपने फ्रीक्वेंसी मॉड्यूलेशन में बेसल फंक्शन नहीं पढ़ा?
सर मैंने असल में उसकी बीपी लाठी की बुक पढ़ी थी ना।
नो सर.
बीपी लाठी में भी
सर
है.
हमने एनालॉग कम्युनिकेशन डिजिटल नहीं की, जस्ट वो बेसिक कोर्स और सिग्नल एंड सिस्टम और कम्युनिकेशन सिस्टम था, वो जस्ट किया हुआ है,
अल्लाह के
मतलब
बंदे,
फिल्टर डिजाइनिंग और ये डीएसपी.
कम्युनिकेशन का जो बेसिक कोर्स है ना, कम्युनिकेशन का अगर सिस्टम्स पढ़ा आपने, उसमें मर के भी वो आपको एम और एफएम पढ़ाते हैं आपको. पर
जी
इसमें हमें टाइम जाया करने का कोई फायदा नहीं है ऐसे काम. आप यही जो मैंने आपको बुक बताई है ना, फंडामेंटल्स ऑफ कम्युनिकेशन सिस्टम्स, ठीक है, इसका चैप्टर 4 है, उसमें उसने पूरा बेसिक फंक्शन को अच्छे से समझाया है, और इसमें एग्जांपल्स भी की हुई हैं कि कैसे आप कर सकते हैं. तो उसका एक टेबल होता है बाकायदा, उस टेबल की हेल्प से आप उसको इन्वर्स निकाल सकते हैं. वो इसमें एक्चुअली वो आप देख लीजिएगा, वो मतलब 2 वे टेक्निक होती है. आप राइट एंड लेफ्ट साइड को बराबर करते हैं, हाँ जी बराबर हो गया, इसका मतलब इसका आर्ग्यूमेंट ये होगा, तो वहाँ से वो आर्ग्यूमेंट निकल आता है. तो लिखते जे इनवर्स है, मगर वो आपको समझ आ जाएगा जब आप देखेंगे.
ओके सर.
अभी तो रिवाइज करें, इसको पढ़ लीजिएगा. मास्टर लेवल पे होगा ना कि अब हर चीज़ आपको नहीं होगी. हम लोग तो अपने स्टैंडर्ड पे चलेंगे ना, यूटी वाले पे, तो उसमें ये है कि आपको जो नहीं है तो कोई नहीं, उसको आप पढ़ लें खुद से, अपने आप को उसी लेवल पे ले आए इंशाल्लाह. So today's lecture, I think today is 30th. All right, 134, 2020 134.
Yes, sir.
Are you present? All right. 2020
Yes, sir.
131, 132, 130.
Yes, sir.
Good. And
Yes, sir.
80. हाँ? आप लोग 4 बंदे हैं ना? All right. 34, 31, 32 and 30. All right. ठीक है.
सर एक पर्सन और भी है,
Yes, sir.
इसका मतलब
उमर
मैं डाउनलोड, मैं ये ना आपकी अटेंडेंस डाउनलोड कर लेता हूँ, वो कंप्यूटर से आई जाएगी सारी, इसमें चक्कर ही नहीं रहेगा. वो यहाँ ना आप डाउनलोड अटेंडेंस लिस्ट भी कर सकते हैं, वो मैंने डाउनलोड कर ली. अच्छा मैं दोबारा रिपीट कर दूं कि वो जो बंदे हैं 134, 131, 132, 130 ये तो पहले ही है, 62 है वो बंदा जो है फिफ्थ बंदा।
यस सर।
यस सर।
अच्छा व्हाट इज द नेम ऑफ दिस रोल नंबर 62 1862?
सर उमर हयात नाम है इसको।
कैन यू स्पीक अप उमर हयात? उमर हयात कैन यू हियर मी? ये 2 दफा एएस कैसे आ रहा है? अब्दुल्ला सलीम अहमद शिराज, अच्छा अकील अहमद, सो हु इज अकील अहमद देन?
जी सर। सर
अच्छा
मैं हूँ
अकील
अकील
अहमद,
अहमद।
अच्छा हाँ ठीक है, अकील अहमद की ट्रेन से लग गई ना। अच्छा उमर हयात से, उमर हयात कैन यू हियर मी? अच्छा वो मेरे ख्याल से उन्होंने अपने आप को ऑफ कर दिया है ना। और बड़ा
जी जी
अच्छा उमर
सुन
हयात,
रहा हूँ लेकिन मेरा नेटवर्क थोड़ा वीक है तो मुझे आवाज भी पूरी नहीं आती है और
अच्छा अच्छा
इसलिए
आप उमर हयात मैं समझ गया कौन है, वो चश्मे वाले ना आप, वो जो आप जर्मनी जा रहे थे वही वाले स्टूडेंट आप?
नहीं नहीं नहीं
अच्छा
सर नहीं।
अच्छा अच्छा पता नहीं, फिर इंशाल्लाह देख लेंगे आपको। ऑलराइट आई विल मार्क योर अटेंडेंस। ऑलराइट थैंक यू वेरी मच, आई विल बी एंडिंग द सेशन। थैंक यू। अल्लाह
अल्लाह हाफिज़ सर।
अल्लाह।